Okay, y'all. Today in class was an absolute sprint. So in this video, I'm going to revisit our lecture notes from section 3.2 on taking derivatives of exponential functions and logarithmic functions and just slow it down. So if you have not had a chance to watch these 3 videos for the prerequisite review of exponential functions and log functions, pause this video now. Watch those review videos, dust off those cobwebs, and then come back here. Okay. But one thing I do want to point out about prerequisite knowledge is how to recognize an exponential function. Because up until now, you've only had power rule. So you know you had a power function. So you knew you were going to use the power rule. Now you're going to have different type of functions that require different types of derivative rules. So your first job is to figure out what kind of function am I taking the derivative of? So just a quick review of power functions. This is what we've been doing with our power rule up until now. A power function is of the form f of x equals x to the b power. Okay, so what is happening? Reading a function all comes down to understanding what's happening to the input. So my input is being sent to a base with a constant exponent. That's what makes this a power function. We have a variable base and a constant exponent. So to find the derivative, we would follow the power rule. That's what we did in this section 2.5 notes. And the power rule says you just drop your exponent in front and multiply with any coefficients that's there. There's an understood 1 coefficient. So I would do 1 times b is b. I would rewrite the base. In this case, it's a plain x. I would decrease the exponent by 1. So whatever that constant exponent is, I just decrease it by 1. And then I tack on the derivative of the base. In this video, we're going to be talking about exponential functions. So an exponential function sends the input to the exponent. So that means we'll have a variable exponent and a constant base. So example 1 here. Example 1, I see my input x is being sent to the exponent and I have a constant base of 2. So if I'm finding, for example, f of 0, I'm going to have the base 2 to the 0 power. If I'm finding f of 1, I'm going to have the base 2 to the first power. If I'm finding f of 3, I'm going to have the base 2 to the third power. The base is constant. It's the exponent that's changing. I have a variable exponent. So then I'm going to have a different rule. I'm not going to use the power rule for this one. I'm going to use the exponential rule. Now, log functions are easy to recognize because you're going to see a log in the rule. So that's more straightforward. You're going to use your log derivative rules. But the difference between a power function and using power rule and an exponential function and using the exponential rule I'm about to show you is a matter of slowing your brain down and asking, where is the input being sent? What is happening to the input? What type of function do I have? That'll tell you which rule to follow. So let's jump over to our exponential rule for derivatives. Okay, these notes have been modified a little bit from what I used in class, but it's the same concepts. Okay, so here is our derivative rule for exponential functions. You can pause the video for a minute and just embrace the horror, because I know these are intimidating, and yes, you need to memorize them, but the more you use them, the more easily that'll come to you. Okay, and we really only have one rule, derivative rule for exponential functions. So then there's a special case. But let's talk about this generic derivative rule first. So we'll come back to that special case in just a minute. Okay, my exponential rule says if you have an exponential function. Now again, that means that the input is being sent to the exponent. You're going to have a variable exponent. And you're going to have some constant as your base. Now, if your function is set up like that, then we'll find our derivative using this rule. So what is that rule telling me? Okay, that rule says, okay, to find the derivative, you're going to start by rewriting the exponential rule exactly as you see it. Then you're going to multiply by the natural log of the base. Whatever that constant base was, you multiply by the natural log of that base. And then you're going to do our chain rule. So the chain rule component in this case is going to be the derivative of the exponent, because our input was being sent to the exponent. So the chain rule is going to tack on the derivative of that exponent. So to compare, let's take a look back at our power function and that power rule, because we're more comfortable with that so far, right? So our power function sent my input to a variable base. So when I did my power rule, the chain rule part tacked on the derivative of the base. So my input was being sent to the base. So the chain rule tacked on the derivative of the base. In my exponential function, the input is being sent to the exponent. So my chain rule is going to tack on the derivative of the exponent. I know this is a lot. Let's see it in action. Okay, let's look at 1a. So 1a is an exponential function. My input is being sent to the exponent. And this is technically a special case because that constant base happens to be the number e. If you remember from algebra, e is the natural number. It's like pi. You know, pi is 3.14159. E is an irrational number that comes up a lot, so it got a special name, the natural number. It's 2.71 something. I don't know. It's a button on your calculator. You can find the decimal value, but it is a constant. So it's going to be a special case, but I'm not going to jump straight to the special case rule. I'm going to use my generic exponential rule because that rule should work in any case. And then we'll talk about why it happens to be a special case. Let's just break down the generic rule. Okay, the generic rule says, I want to find the derivative of an exponential function. What do I need to do? So I'm coming back up here to this generic rule. Okay, I start by rewriting the exponential rule. I'm going to rewrite 3e to the x. Right here. 3e to the x. Then I need to multiply by the natural log of the base. So in this case, my base was an e. I had a constant base e. So I need to tack on the natural log of e. And then I need to do my chain rule. My chain rule says I'm going to take the derivative of the exponent. My input went to the exponent. That's what made this exponential. So I'm going to tack on the derivative of my exponent. Well, the exponent in this case is just a plain old x. And when we learned the power rule, we all agreed that the derivative of a plain old x is just 1. So that's going to hold true here also. Okay, now why is this a special case? Let's come look at this special case rule. Okay, there's really only one difference in this special case. So let's look at the rule. So over here in my generic case, I start by rewriting the exponential rule. Well, in this special case, I do the same thing. Whatever my exponential rule was, I rewrite it. I also see the derivative of the exponent there is part of the chain rule. The thing that's missing, the thing in the middle that's missing would be the natural log of the base, which happens to be an e. But from algebra, you learn the natural log of e is 1. You can verify that on your calculator because you have a natural log button and an e button. So it's like that natural log step. We didn't need it in this special case, but everything else is the same. So you don't really need to memorize this special case. You just need to know that the natural log of e is 1. But if you know that, it's going to just streamline this derivative rule process. And that's always nice. Save some energy there. Okay, so let's just clean this up knowing that rule. We know the natural log of e, that's just going to be 1. So if I go to clean up this derivative rule, what am I really going to get? Okay, I'm going to get 3e to the x times, instead of the natural log of e, that's just going to be 1, times, instead of the derivative of the base, we just decided the derivative of x is 1. So my derivative is just 3e to the x. I could get that same answer if I followed this special case rule. Okay, let's do the special case rule just to see that we're going to get the same answer. Okay, so starting over using my special case rule. So my function was 3e to the x. Okay, the special case rule, coming back up here to my special case rule, it says, what does it say? It says the first part of the derivative is rewriting the function rule. Well, here's my function rule. I'm going to rewrite it. That is 3e to the x. Then my rule says I need to tack on the derivative of the exponent because it's an exponential function. So when I go to do that, when I go to tack on the derivative of the exponent was just an x. The derivative of x is just a 1, so that's not really there. So see how I end up getting that my derivative is just 3e to the x. I just skipped this natural log of e step, the natural log of the base. But if you're worried about too much to memorize, you do not need to memorize that special case. You only need to memorize the generic rule, and it'll lead you to the special case. Okay, let's do another example here. Let's do B. It's exponential, right? My input is being sent to the exponent. And in this case, my exponent is not a plain x. So my chain rule is going to be a little bit more interesting. But let's go ahead and do our steps. So the exponential derivative rule says you start by rewriting the expression. Okay, so I'm going to do e to the 3x. I multiply by the natural log of the base, which is a base e. And then I tack on the derivative of the exponent. My exponent is 3x. So if my exponent is 3x, then to find the derivative of that, I need to use my power rule. And I'll see that the derivative is just a plain old 3. So what do I really have here? I have the derivative is e to the 3x times, well, the natural log of e is just 1. So times 1 times the derivative of the exponent, that's just 3. So if I clean that up and rewrite everything here, that's going to give me the derivative is, well, order doesn't matter when I multiply. Multiplying by 1 doesn't matter. So I'm going to put the 3 in front of the e to the 3x just for clarity's sake. Okay. Let's work number 2 now, where it's not a special case. It's still exponential. My input is still being sent to an exponent, but my base is not an e. So we're going to follow our general rule here. I rewrote it for clarity. So my rule says you rewrite your exponential expression. So whatever this exponential expression is, I'm going to rewrite it. That's 2 to the x. Then I tack on the natural log of the base. Well, my base in this problem is a 2. So I'm going to have natural log of 2. And that's just some decimal number on my calculator. So I'm going to leave it in this form. Then I have to tack on the derivative of my exponent, which is a plain x, which we know is a 1. So the derivative of 2a is just 2x natural log of 2. And again, order doesn't matter, but I'm going to write the log at the end just so it doesn't get confused with that 2x. Let's look at this next one. Okay, it's exponential. I'm going to follow my rule. My rule says I rewrite my exponential expression. That's going to be 3x squared.